Hello! Today we're going to see chapter 3 of the tutorial. So, basic classes. This chapter is going to look to some of the most fundamental building block that it's important to know in order to work with Adam's Tower. And we start with num. That is the main numeric type suggested by Adam Tower. And it's a pretty powerful numeric type. In Java you have 32-bit ints. In Python you have arbitrary precision integers. In JavaScript you have floating point numbers as the suggested main type of number. In 42 you have arbitrary precision rationals, so that you can represent an arbitrarily large fraction. You can have a little number, 1, 2, 3. You can have a number that is still little, 4, 5, 6, 7, 8, 9, 0. You can have a very big number that will probably get out of the boundary of the int 32. And you can have a big number with a little delta, and this could not be represented precisely with floating points. And then you have the possibility of just writing arbitrary fractions. Again, if you want to use the slash for the division or the minus, you should use the string syntax, but nothing changed in the value that you are creating. All of those other ones can also be created with the string syntax if you prefer, and that will be absolutely the same. Then you can print your fraction, and it will print it normalized. So in this case, the form that we put it in input is already the normalized form, but if we have a fraction like 12 divided by 4, it will print it as 3. Another useful numeric type is I, and I stands for index. And yes, it is a 32-bit int, and you can definitely use it if you want to work with 32-bit ints, but in 42 you don't really have many good reasons to work with 32-bit integers, except when you work with index of collections, and that's why we call it index. So you want to take the element in position 5, that's an index in the collection. We have other numeric type, we have double. So 64-bit floating point and mat.long, 64-bit integer, that are used even more rarely. When designing Adam Tower, I made a conscious decision to not offer 32-bit floating points, because right now with all modern machine being 64 bits, you get very little benefit for a lot of loss precision. We have a lot of different kinds of conversions, and so you can, for example, convert an integer into a double just by trying to construct a double and taking in input another numeric. So you can call double of an index, you can call double of a num, you can call double of a mat.long. Using just numbers is still often a bad idea, because your numbers probably represent something specific. And so in 42 we have the unit library, and with the unit library we can define our own unit of measures. So for example, here you see we are loading the library unit, and we call the loaded library unit, but we could use any other name, I can make a year, where a year is a unit of the index. And that's because we don't really need arbitrary precision rationals for years. The years are always, integer numbers and reasonably small. And then I can have a person that can have a string name and a year age. In this way, we can have a person that is 25 years old. Using the library unit, help us to avoid mistakes. So, for example, we can have 3 years plus 2 years equal 5 years, but we cannot multiply 3 years by 2 years. We can instead multiply 3 years by the support, so 2i, to get 6 years. In this way, by defining our own units, we can leverage on the type system to help us to not do mistakes, to follow the logic of our application by lifting our assumptions as new classes. Our unit library also offers a wide variety of units from the International System of Units, and we can create them like this, with this confusing syntax that we will explain more later. But generally the idea is that unit have a trait International System of Units that have a support. And the support is what kind of a number we want to use to represent our units. And so here we choose num. And so we have our class system of units that inside is going to have meter, kilogram, seconds, and so on. And we can do operations summing meters and multiplying it by num, the support that we have chosen. We can divide 2 meters to get a number that is like a pure unit. We can also hackingly extract the inner number by calling hash inner. We use the hash in the name of this method to warn the user so that they can check that they are doing the right thing. Here there is some interesting code that I'm not going to go through. They show how you can use units to build a rocket and see if the rocket can make you fly if it has enough thrust. And then we can move to alphanumeric. And alphanumeric is like the same kind of concept of unit, but for stringy stuff. So in 42, we don't just write strings with the quote. We have to put the type in front. And in this way, we can have so many different kinds of strings. And all of those kinds of strings can be created using alphanumeric. So for example, we want an email, and we create it using the alphanumeric decorator. So s.alphanumeric, and then we add some fields. So we have a local and a domain. And alphanumeric want us to write a class method that takes a string parameter and returns this. And in this way, alphanumeric knows how to build those instances from a string. So here, for example, we take our string, we check the index of on the at, then we get a certain index. If the index is exactly -1, we can throw a parse error. Otherwise, we can take the local as string.substring 0 to the index, and the domain as string.substring index plus 1i to the size of the string. We can do some more checking. If the domain contains the at, we can throw another parse error. And finally, we can create the actual object. And so, since we are in alphanumeric, we will have to provide a string that represents the normalized string form for our alphanumeric, and all the fields that we are manually declaring. And then we can use this class by using email of arthurdent@gmail.com, and then I can do myemail.local and check it is Arthur Dent. I can check for the domain and see that it's Gmail, and I can print the toString and get arthurdent@gmail. We can have a normalized email where, for example, in Gmail, you can have as many dots as you want and your email doesn't actually change. And so we can represent this in our alphanumeric class by replacing all the dots with the empty string in our local. And so our normed email is now a string interpolation that contains local, the @ symbol, and the domain. And by using the normed email there, we will get as toString just arthurdent without the dot. Enumerations are also a useful data type to use to model the domain of our problem. So for example, here I have direction equal collection.enum of north, east, south, and west. That is, enum is a decorator, and we pass a class with nested classes with names for our enumeration elements. And the decorator will add a vals nested class that is a list of all our elements. And we will have constructors for our enumeration elements. We can iterate on all of the elements in the vals of our direction, so all four of them will be printed here. We have, of course, all our equal, different, toString, and so on. Enumerations in some languages are very, very poor. They are basically just constants and nothing more, and you cannot do a lot with those constants. Java opened the way a few years ago for more interesting kinds of enumerations where you can actually have methods in your enumerations. And 42, or if you prefer Adam's towel, is following on this idea. And so you can have in your directions methods. So for example, you can have a method this opposite that returns the opposite direction. In north, we can define a method that returns this one, so a direction, opposite equal south. In east, I can have an opposite of west. In south, I can have an opposite of north. And in west, of course, I can have an opposite of east. And if you want more methods, you can just put them there. And the idea is that direction is going to be an interface that is implemented by those classes. Now, the summary part is possibly the most important part here, albeit it's quite short. The idea is that Adam Towel gives you this rich support for defining your own specialized data structures, instead of just having to rely on the default provided one. And this is important. When you code in 42, you want to leverage on the type system to support you so that the type system prevents you from doing bad behavior, for doing something that you have not predicted, that you didn't intended. So instead of using a lot of ints and strings everywhere, in 42 you can define your alphanumerics for all the different flavors of the strings. And you can define all of your unit of measure for all the different kind of reasons for which you're using number stuff. And you can use modifiers to make sure that you use objects only in the way you intend. And you can use capsule and capsule mutators to make sure that you properly encapsulate the reachable object graph. Basically, what you are doing in 42 is that you are vaccinating your code against certain bugs. You have to go through a little bit of effort, when you have a vaccine, you need to go book to the doctor, decide to go there, take the appointment, find the right moment. Sometimes you have to pay some money, and then you will get immunity to a certain kind of illness. And this immunity is overwhelmingly more valuable than the effort that it takes to get the vaccination. And in 42, it's the same. By taking this little extra cost at the start and paranoidly protecting our code from all the possible way in which it could be misused, we are actually building a significantly more secure environment. And if you're working alone on a project that you can finish in 24 hours, yeah, this is not going to be particularly important. But if you are working on a very long-lived project where most of the development time is maintenance, or you are doing a project where you're working with a lot of other people that you don't know or trust that much, for example, because they contribute on your code on the internet, or you are working with a lot of third-party libraries that you don't really control and you cannot possibly review every time they get updated, then this is the way to get a modular reasoning. You can actually control the scope of your reasoning. You can write the code so that every method, or maybe every class sometime, or maybe a couple of tightly connected class that work all together, and you can reasonably fit all in your head at the same time. You can look at them and you can see that modularly, they work. That is, no matter what is the context you put this code into, there will not be a breakage in your assumptions. Maybe your code will not compile. Maybe your code will throw an error at runtime, but your code will never do something unpredicted. Your code will never do the wrong action. And this is in general the main philosophy of 42 that will be explored a little bit more in the next chapter, errors and exceptions. See you for the next chapter in a few more days. Bye!